We now continue our discussion of statistical testing. So far we've kept our discussion of statistical testing quite general. Now it's time to finally return to the linear regression model. We continue to use our old example of the income effect of the cost of education. Beta 1 is the causal effect of the cost of education. It is the population parameter that we want to learn about or that we want to conduct statistical inference on. To use the toolbox of statistical testing to learn about beta 1, we have to construct a test. And to construct a test, we need three important ingredients. First, we need a null hypothesis. Then we will need a test statistic. And finally, we need a decision rule. We consider the null hypothesis that beta 1 is equal to 0. Economically, this means that there is no causal effect of the cost of education. Recall that we are setting up the null hypothesis in order to reject it or in order to disprove it. So with this null hypothesis, what we really are trying to show is that there is a causal effect of the cost of education on income. Instead of setting the causal effect to 0, we may want to set it to a different fixed number. Let's just call it beta 1 H naught. What is important about this number is that it is fixed by the researcher. This allows us to also use this kind of null hypothesis to express the idea that the true causal effect is equal to, for example, 3. And then we can go ahead and try to disprove that. But now for this example, we work with a hypothetical value of 0. For a test statistic, we can use the following t-statistic. We take the OLS estimator. We subtract the causal effect that we assumed under the null hypothesis. And then we divide by the standard error of the OLS estimator. The t-statistic is a really great choice here for at least two reasons. The first reason is that it is a measure of discrepancy between what we believe about the causal effect based on the sample. This is the causal effect that we estimate, and what we have hypothesized about the causal effect. If we are estimating a much larger value than we have hypothesized, then the t-statistic will be a large positive value. If we estimate a much smaller value than we hypothesized, then the t-statistic will be a large negative value. If the estimated value and the hypothesized value are fairly close, then the t-statistic will be small in absolute value. The second thing that is so great about the t-statistic is that it is pivotal. A test statistic being pivotal means that we can completely describe its behavior if the null hypothesis is true. What is the distribution of the t-statistic if our null hypothesis is true? If the null hypothesis is true, then the true value is identical to the hypothesized value, which means here we can just replace the hypothesized value by the true value, beta 1. This means, in this case, the t-statistic is recentering by the true value, and we end up exactly with the standardized OLS estimator that we've already discussed. And we know that the standardized OLS estimator has approximately a standard normal distribution, at least in large samples. This proves that the t-statistic is pivotal, or at least approximately pivotal in large samples. So all that's left now is to define a decision rule. For what values of t do we reject the null hypothesis? We've already discussed that large absolute values of t indicate that the null hypothesis is false. And a large absolute value means that it is far away from 0. It could be positive or it could be negative. So let's reject if the absolute value of t is large, specifically if it is larger than some number c. And we call this number c the critical value. What value should we choose for c? In general, we like a small value of c because that means that the test will reject more often, and a test that rejects is a powerful test. On the other hand, we don't want c to be too small so that we reject too often. How can we reject too often? Well, that's only really relevant in the setting where the null hypothesis is true. Then every time we reject, we commit a type 1 error. So if the null hypothesis is true, choosing a smaller c increases the probability of type 1 error. We want to define a decision rule that makes sure that this probability is not too large. This is called controlling the size of the test. And particularly we say that the size of the test is supposed to be alpha, where alpha is a small probability that is specified by the researcher. This implies that our critical value should depend on alpha. To determine the exact numerical value of C alpha, note that for size control, the only scenario that is relevant is that the null hypothesis is true. So we only have to worry about scenarios where this condition is satisfied. And under this condition, we know exactly what the distribution of the t-statistic is. It is a standard normal distribution. The density of the standard normal distribution is the Gaussian bell curve that kind of looks like this. Let's say that we choose C alpha to be this number. For what values of the t-statistic t do we reject? Well, we certainly reject if t is larger than C alpha, so any of these values. But then another way of making the absolute value be really large is to have t be a large negative number. So we also reject if t is smaller than minus C alpha. In summary, we reject for any of these values of t. Under the null hypothesis, this is the distribution of the test statistic. So the probability of rejecting is the sum of this area and this area. These two areas are exactly the same because of the symmetry of the Gaussian bell curve around 0. The sum of these two areas gives the probability of rejecting if the null hypothesis is true. Therefore, it gives the size of the test, and we want to control the size to be alpha. The sum of these two areas will be alpha if each of those areas is alpha half. We have now completely defined C alpha. C alpha is the value with a property that a standard normal realizes with probability alpha half to a value larger than C alpha. Or equivalently, a standard normal realizes to a value of smaller than C alpha with probability so it would be 1 minus alpha half. The unique value with this property is called the 1 minus alpha half quantile of the standard normal. As a notational shorthand, we use the following notation for quantiles. We write phi minus 1, indicating that we are just inverting the distribution function of the standard normal. And then here we write the probability. In our case, that would be 1 minus alpha half. This is our definition of the critical value. We have now completely defined the test. The test that we have constructed here is called the two-sided t-test. Let's recap all the ingredients of the test, just to make sure that everything is working as intended, and also to illustrate how a researcher would apply this test in practice. Before applying this test, the researcher has to make some decisions. First off, they have to decide on the hypothesized value. What value they would choose here will depend on the theory that they want to test. For example, we chose 0. So we wanted to test the null hypothesis that there is no causal effect. And this gives us the opportunity to show that there is a causal effect. Our model had only one regressor and therefore also only one slope coefficient. If you have a model with several regressors, you have several slope coefficients, and you may want to choose a different slope coefficient here. So there could be a beta 2 or a beta 3 here. Then we also have to decide on the nominal size of the test. A researcher who chooses a large alpha risks a large probability of type 1 error. A researcher who chooses a small value of alpha will face a smaller probability of type 1 error, but will also have a test that in general rejects less often, that is more conservative. That means the test is less powerful. These are all the decisions that we as researchers have to make before we can apply the two-sided t-test. Now we are ready to apply the t-test. We need a random sample, and usually we would just use the estimation sample that we've used for OLS regression. On this sample, we compute the OLS estimator and its standard error. We already know the hypothesized value. So we have all the numbers that we need to compute the t-statistic on our sample. We get a realized value of the t-statistic that we can compare against the critical value. Now we know whether the test rejects or not. If the test rejects, we conclude that our null hypothesis was incorrect, just as we did before. Now that we have defined a test, we want to study its statistical properties. The properties that we are interested in are its size and its power. We start with size, and the way we're going to study the size of this test is by simulating the empirical size. We already know that in order to draw simulated samples, we first have to specify a population. We will define this as the population model. We have to decide on concrete values for beta 0 and beta 1. We just use the values we already used previously. 40,000 for the intercept and 3 for the causal effect. Now, to conduct the two-sided t-test, we have to specify the null hypothesis, and since we're interested in simulating size, we have to specify a true null hypothesis. So our null hypothesis will be that beta 1 is equal to its true value, 3. We also have to specify the nominal size of the test, alpha, and we pick alpha to be equal to 10%. Before I show you simulation results, let's take a moment to consider why the nominal size may be different from the empirical size of the test. Obviously, our test aims for the nominal size to also be the empirical size. Why may this not work out in practice? We have derived the test under certain theoretical considerations. What were these? Well, we assumed that this normal approximation is exact, which it is not. And this could be a problem in particular if the sample size is really small. To investigate to what degree it is a problem, we will simulate different sample sizes. This animation summarizes the simulation results for different sample sizes. The smallest sample size is 20 and the largest sample size is 200. The panel on the right-hand side shows the simulated empirical size for different sample sizes. We already know how to interpret such graphs. We know that there is simulation error that can lead to small deviations of the simulated values from the true values. However, the big picture painted here should be pretty accurate. So what do we have here? The nominal size of the test is 10%. This is how often we want to reject if the null hypothesis is true. We see that in practice we are rejecting a little bit more often. We say that the test is oversized. This is really severe for the small sample sizes. This is not surprising because we know that the normal approximation needs a decent sample size. If we look at the moderate and large sample sizes, we can see that already for sample sizes less than 200, the empirical size is very close to the nominal size. This shows that for larger sample sizes, the t-test works in the sense that it has the size that you want it to have. Most datasets that you encounter in economic research are large enough that you don't have to worry about the t-test being oversized. The t-test has reliable size control. Now that we've covered size, we move on to power and we simulate the power of the test. Power is all about scenarios where the null hypothesis is false. Therefore, we want to simulate beta 1s that are different from the value that we hypothesize. We simulate beta 1s between 3 and 5.5. For this exercise, we're mostly interested in learning how the test behaves under different beta 1. To keep things simple, we keep the sample size fixed this time around, and we'll fix it at 150 observations. This animation summarizes the simulation results. In the left-hand side panel, we see the simulated distribution of the t-statistic. If beta 1 is equal to 3, then we are operating under the null hypothesis. In this case, the distribution is well approximated by a standard normal. We already knew this. If beta 1 is larger than the hypothesized value, then the center of the distribution moves to the right. This means large values of the t-statistic become more likely, and small values of the t-statistic become less likely. As a result, we are moving a lot of probability mass to the right of the critical value, that is into the region that is here shaded in yellow. As a result, rejection becomes more likely. Let's take a closer look at how moving away from the null hypothesis changes the distribution of the t-statistic. Under the null hypothesis, the distribution is standard normal. Now under the alternative that beta 1 is equal to 5.5, we have this distribution. It still looks normal, and it really looks as if we have just taken this distribution and shifted it here. So it looks as if there is just a change in location. That's not exactly true. The variances of these two distributions are not exactly the same, but they are almost the same. I really want you to focus on the change of location. Let's call the distance that we have traveled here delta. And this is the same delta as we have on the x-axis of this graph. Delta is equal to the true beta 1 minus the hypothesized value, in our case that's 3, divided by the standard deviation of the OLS estimator. This formula maps every beta 1 into a value of delta. For example, if the null hypothesis is true, then beta 1 is equal to 3. We have 3 minus 3, so delta equal to 0. So we would be here. Now the probability of rejection at delta equals 0 is very close to our nominal level of 10%, which is exactly how we like it. Beta 1 larger than 3 are in the alternative, and they get mapped to delta values that are positive. All these delta values correspond to beta 1 larger than 3. So this axis here represents different alternatives. What do we care about if we are in the alternative, that is, if the null is false? then we care about possibly not rejecting and committing a type 2 error. We can use this plot to read off the probability of type 2 error. Suppose we are facing a beta 1 that corresponds to this delta. This graph plots the probability of rejection. Therefore, the probability of rejecting the null hypothesis is equal to the length of this line segment. The probability that we do not reject is the remaining probability and equal to the length of this line segment. It is easy to see that the probability of type 2 error will depend on where we are in the alternative. If we are here, that means beta 1 is very close to 3, then the probability of type 2 error is fairly large. If we are here, that means beta 1 is much larger than 3, then the probability of type 2 error is very small. This is quite intuitive. The further we are away from the null hypothesis, the easier it becomes to find evidence against the null hypothesis. Instead of considering different alternatives, let's fix the alternative, and let's say beta 1 is equal to 5. This means the numerator here is 2. And let's say that the standard deviation is 1. Let's just assume that. That means the delta is 2, and we end up here. The probability of rejecting the null hypothesis, and therefore the power of the test, is this number. How can we increase the power of the test? To increase the power of the test, we want a larger delta, because for larger delta, we have the more powerful tests. Since this is fixed, the only way of increasing delta is to decrease the standard deviation of the OLS estimator. How do we do that? We know what the variance of the OLS estimator looks like, at least under the additional assumption of homoscedasticity, and we understand all of the components that feed into it. We can make the variance, and therefore the standard deviation, smaller, for example by increasing the sample size. This means if we have a larger sample, we decrease the standard deviation, and therefore increase delta, and we move in the direction of more powerful tests. In summary, if we have access to a larger sample, the two-sided t-test becomes more powerful. This is quite intuitive. If we have access to more information, we should be able to learn more about the true causal effect. And in statistical testing, learning means rejecting.